relations and functions. Okay. So a relation, the definition of a relation is basically any set of ordered pairs that are related in any way. So when you think about it, anything is a relation if you can write an equation for it. So over on the wall there, y equals x squared, y equals 1 on x, y equals x cubed, x squared plus y squared is the radius squared. I mean, a relationship exists. So they are all relations. So, there's my example, a circle. X squared plus y squared is 25. We're probably more interested in functions, to be honest. Now, a function is a special type of relation that has this one-to-one relationship. In other words, there's a maximum of one y value for every x value. Okay? So y equals x squared, I guess, is our classic example of a function. Visually, we can use what's called a straight line test. Okay? So if you get a vertical line, or a ruler if you like, and you slide it along vertically, and it only ever hits the curve once, if at all, then it is a function. So when we look at our parabola, get a vertical line, yep, only hitting it once, it's all good. Hyperbola, yep, hitting it once, hitting it once, hitting it once. Hang on, I get to the y-axis. Doesn't hit it at all. That's okay. Now it starts hitting it again. Fine, that's a function. Cubic, a function. Circle, you start at the circle. No, it doesn't touch it, doesn't touch it. You get to the circumference, hits it once, that's okay. But then as soon as you go any further, hits it twice, no good, not a function. Okay? So visually, that's, I guess, the easiest way to work out whether something is a function. So there we go, here's our hyperbola. Oh, look, doesn't matter where I put the line, only hits it once. Yes, function. X equals y squared. No good. No, not a function. Now, this one's interesting. X equals y squared. It's actually made up of two functions. And one is y equals the positive square root, which would be the top half of the parabola, and y equals the minus square root, which would be the bottom half of the parabola. Let's talk about domain and range, two very important features that we look at. So domain. Imagine our function, or relation for that matter, is like a machine. And we're going to input values. And answers will come out. Well, the input is the domain. All the possible values we can throw into this machine and get an answer. That is our domain. So to find the domain. Now again, if you've got the picture, it's easy. You can just look at it. And you can see as you go along horizontally, are there any breaks in the curve and things like that. Very easy. But if you don't know what the picture looks like, then when you look at the function, sometimes it's actually easier to find things that x can't be than trying to work out what x can be. So here's x equals y squared again. Looking at the picture, nice and easy. Domain, x is greater than or equal to 0. It only exists for those x values. But one like this, the domain is x is less than or equal to 0, less than or equal to, because of course the endpoint is coloured in. But on the other side, it's just greater than because the endpoint is not included. So x is greater than 2. Okay, so we don't know what the picture looks like. What do we look for? Fractions. If there's a fraction in the function, the key thing about a fraction we know, bottom of the fraction can't equal 0. That's a key thing. So I can't substitute 0 into the bottom of this fraction because it won't give me an answer. So I know x can't equal 0. Now we do not write a domain like that. Maybe this is what you're thinking about. Because a domain is what values of x are included, not what's excluded. If I wrote x can't equal 0, that's telling you what's excluded. It's not telling you what's included. So that's where I would write, oh yeah, look, I can put in any real number, except I can't put in x equals 0. Now, don't get too hung up about this because there's a bit of grammar there, because I could also write all real x except x can't equal 0. Because when you think about it, it's just grammar. All real x, except x can't equal 0. Or am I saying all real x except x equals 0?
Oh.
You see what I mean?
Yeah.
So it doesn't really matter. Yeah, I tend to write it this way. So except x equals 0. Y equals 1 on x squared minus 1. So again, the key is bottom of the fraction can't equal 0. So simple little thing to solve. Well, x squared minus 1 can't equal 0. So x can't equal plus or minus 1. So yeah, in this case, again, I'd write, okay, well, look, I can put anything in there, all real x, except I can't put in plus or minus 1. Can't put in plus or minus 1. If I've got two fractions, well, both fractions still have to obey the same rule. So x minus 1 can't equal 0, so I know x can't equal 1. 7 minus x can't equal 0, so I know x can't equal 7. So all real x, except I can't put in 1 and I can't put in 7. Okay, root signs. Can't find the square root of a negative number. Okay, that's a basic rule there. Can't find the square root of a negative number. So if I have y equals the square root of 4 minus x squared, I know 4 minus x squared is greater than or equal to 0. Now the solution to that, x squared is less than or equal to 4, so x is in between minus 2 and 2. So in this case, you'll notice I haven't written all real x, because I'm simply writing down what's included. The other one, I wrote down all real x because what I found was what was excluded. So they say, yep, I can put in anything except these ones. Whereas this one, I'm saying, no, it's just these numbers. These are the only ones I'm going to deal with. By the way, what shape's that? Yeah, semicircle. Yeah, so you're basically talking the top half of a circle there. And that's why its domain is plus or minus the radius there. Two square root signs, both of them must be true. So I know x must be greater than or equal to minus 3, but it must also be less than or equal to 5. Both must be true. So I'm looking for all numbers that are greater than minus 3, but less than 5 for that particular one. Oh, this is where we combine the ideas. Because, okay, I got the square root sign, so I know x plus 2 has to be greater than or equal to 0. However, it's on the bottom of a fraction, so it can't equal 0. So it's simply just x plus 2 is greater than 0 in this case. So x is greater than minus 2. Range then. So domain, the input. Range then is the answers. All the possible y values you can get by substituting in the entire domain. If you were to throw in every possible number that you can, what do you get out of this function? What comes out? So again, visually, very easy. This time I'm imagining I'm climbing up the y-axis and having a look to see if there's a curve. Yes, it's there. You'll view it. Whoop, yep, I can still see the curve. Oh, I'm actually meeting it. Here I am at the origin. Keep going. Whoop, yep, oh, still there. So range, all real y. Our step function over there, in this case, y is less than or equal to 1 and y is greater than 3. By the way, when you are writing domain and range, when you said all real, you do mention all real y or all real x, because you need to let them know that you understand that it's the x values for the domain and the y values for the range. If you just wrote all reals, they'd go, yeah, do you mean the x values? Do you mean the y values? Right, so all real y. So things to look for, range. Maximum and minimum values. So keep in mind things like this. If you've got an even power, so x squared, x to the 4 and so on, or an absolute value, they've got to give you positive answers. Can't give you a negative. So the very basic one, y equals x squared, I know that, hey, that will never give me a negative answer. In other words, the range has to be y is always going to be greater than or equal to 0. But if I was to just add 3 to this whole thing, well, now my answers must be greater than or equal to 0 plus 3, because the x squared has to be greater than or equal to 0, but we're adding 3 to everything. So range is greater than or equal to 3. 5 minus x squared. Well, because I'm now multiplying by a negative, then the minus x squared is always going to give me a negative answer. So this one will always be less than or equal to 5 minus 0. So there's my range. Absolute value of x plus 2. Again, which absolute value has to be greater than or equal to 0. Absolute value, but now I'm subtracting 5. It's the same sort of idea. That one's y is greater than or equal to minus 5. Again, knowledge of the basic curves makes it so much easier. So if you know what the picture is, you just go, oh yeah, right, that's your domain, that's your range. You have restrictions on the domain. So like you say, you might have found the domain and there is a restriction on it, or they might have a question where it's just a piece of the curve you're looking at, and they're saying, only look at it from here to here. Okay, so what do I do? I'll have a look at the endpoints. So many of these, other than the ones where they actually give you the domain, if it's a restricted domain, you'd be surprised how much symmetry plays a part. So I'll often have a look at the midpoint as well. And it'll give me a feel for the range, what's happening with those numbers. So here's y equals 4 minus x squared. Yep, okay, we know it's a semicircle. Let's pretend we don't. The domain was restricted, minus 2 to 2. Well, when I sub in 2, I get 0. Also, because it's squared, when I sub in negative 2, I'd get 0 as well. And in the middle, I get 2. Now, it's a pretty fair bet that that range is going to go between 0 and 2. Now, if you feel uncomfortable, sub a few more numbers in and get a feel for what the curve's doing. Yeah. So our range is in between 0 and 2. Fractions. If you have a constant on the top of the fraction, then the fraction can't equal 0. Right? It's impossible to divide a number by something and come up with nothing. So, all right, pretend we don't know what it looks like. Y equals 1 on x. Well, we know the domain. We've worked that out. The range, oh, look, constant on the top of the fraction. So it's impossible to get the answer 0 for that fraction. Can't happen. So all real y, except y equals 0. 5 plus 1 on x. Well, that fraction can't equal 0. So it would be impossible to get 5 plus 0. So all real y, except y equals 5. Ooh, x plus 7. It's not a constant on the top of the fraction now, you'll notice. So what do I do here? Well, yeah, I do. Well, it's a simple little polynomial division, but at the end of the day, it's a polynomial division. But I could rewrite that fraction as 1 plus 3 on x plus 4. I've now got a constant on the top of the fraction. So that particular fraction can't equal 0. So y can't equal 1 plus 0, or real y, except y equals 1. A little bit about function notation. Very common we use f. I guess f for function. I mean, you can use any letter you like. Function x is 3x squared plus 4. So if I want to find function 5, I just substitute 5 everywhere I see x. Pretty simple, really. But of course, it could be another pronumeral. Function a, oh well, everywhere I see an x, I'll put an a. 3a squared plus 4. Or I could have something really fun like this. Function x plus h minus function x. So, everywhere I see an x, I'll put an x plus h minus, the original function itself. Expand out, tidy up. There we go, 6xh. That will become very familiar. All right. That's enough of me talking. I've already sent one person to sleep, so...